Hello, I'm Lachlan Mayers, and I'll be presenting on behalf of our team from the University of Adelaide and the Australian Institute of Machine Learning, consisting of Stefan Podgorski and our principal investigator, Reid. I'll be covering the work titled Learn to Rage, Experiencing the Emotional Rollercoaster that is Reinforcement Learning, which summarises our team's submission to the 2022 Learn to Rage Challenge. For Stefan and I, this challenge was our first attempt at reinforcement learning beyond cartpole. The work's title is a description of that journey. During this presentation, I would like to start with a background on the Learn to Race challenge, then talk about our attempts to solve the challenge using reinforcement learning. And following that, the agent we submitted for the challenge round 1, and then a modified version for round 2, and then finish up with a short video of the agents going head to head. The objective of the Learn to Race challenge was to push the boundaries of autonomous technology while still maintaining a focus on safe operation. The goal of participants was to create the fastest agent possible that could both generalise to unseen tracks and comply with safety standards. The organisers provided teams with a racing simulator containing 2 test tracks and a robo-race car. The simulator allowed users to receive RGB images and vehicle velocity and send steering and acceleration commands at a rate of up to 10 Hz. The competition consisted of 2 rounds. In stage 1, participants developed and evaluate their agents on Thruxton circuit, which is included with the simulator. In stage 2, participants are evaluated on an unseen track, the Vegas North Road circuit. Evaluation consists of 1 hour practice period, then 3 laps of the circuit.
In the first approach, the Soft Actor Critic provided in the competition was used as a starting point and then modified to add temporal information using flare instead of frame stacking. Flare is a modification to the variational autoencoder, which takes the difference between the current and past latent representations, which are then fused by concatenation to the current latent representation. This version of SAC with flare was used as our baseline. Due to the default reward function, the Learn to Race SAC baseline agent tended to learn to zigzag over the center line to maximize reward. The zigzagging action limited the safe maximum speed of the agent. So to encourage the agent to drive a less zigzag motion, a steering penalty was formed and added to the default reward at each time step. The steering penalty was a handcrafted function of the steering angle and the vehicle's current speed, which was small for low speed and small steering angles, and large for high speed and large steering angles. As this is a competition for driving fast, the agent also needed to be encouraged to drive quickly. To that end, another handcraft function of segment time was added to the reward function at each time step. The cumulative effect was that the agent was penalized for spending a large amount of time in a segment for each segment. The segment time was a timer which started at the beginning of each segment. Each figure shows the results for the baseline agent with slow and fast frame rate and the shaped rewards with steering, segment, and combined penalties. The results show that for the agents trained with the reward shaping, there was an increase in validation return, movement smoothness, and trajectory stability for the combined penalty, but disappointingly were slower than the baseline SAC agents. Round 2 of the competition had entrants compete on an unseen track, so it was important to have an agent which was able to generalize to other tracks easily. To assist the agent to generalize easier, the input cropped images were pre-processed to extract features that describe the geometry of the observation for any track irrespective of specific pixel values. The methods of pre-processing were canny and Sobel edges and RGB representations of optical flow. These pre-processed images were then input into the variational autoencoder to produce latent vectors from the abstracted images. With the new image representations, the variational autoencoder needed to be modified to accommodate the new inputs and their combinations. The variational autoencoder was modified by adding more convolutional layers, residual connections on the encoder and decoder while preserving the bottleneck, mesh activation, and batch normalization. Batch normalization was also applied to the bottleneck layers to improve training and inference stability. The figures show our baseline SAC and their agent trained with canny edges only and a combination of RGB optical flow and Sobel edges. Despite the good image reconstructions of the modified variational autoencoder, the agent showed marginal improvement. The validation return and total distance were generally higher, but again the average speed was slower than the baseline method.
As hard as we tried, we could not solve reinforcement learning in a continuous action space on the first project. Turns out it is a really complex problem to solve. We decided to explore a more traditional approach in which visual percepts were used in combination with rule-based controllers. The resulting system required less training, was more explainable, generalised better, and was way easier to tune. The perception system used a deep neural network to infer semantic information from incoming images. From this information, it calculated drivable areas and lateral track position. The control system used the information from the perception system to create and follow an optimal path at a best achievable velocity and at all times considering track boundaries and safety margins. Rather than seek to use an advanced controller like MPC, we opted for a simpler controller that worked directly from the image frame. The steering and acceleration controllers relied heavily on an accurate semantic segmentation. For this task, we trained a semantic segmentation network to classify image pixels as either road or not road. There was very limited information about the Las Vegas track, only a couple of images that indicated the imagery would be much different than the Thruxton and Anglesey circuits. To combat this, we trained our model on grayscale images with as many augmentations as possible. This proved an effective strategy as no additional training was required during the 1-hour training period allocated for round 2. With semantic information available, an algorithm was then used to calculate coordinates representing an optimal path. These coordinates were used for both steering and acceleration controllers. The image in the upper right has squares marking the upper and lower bounds considered for the calculation of relative steering angle. The points considered for calculation of this angle were varied based on the vehicle velocity. The relative angle was then fed to a PID controller to produce the steering command. To compute acceleration, the coordinates were split into discrete chunks, with each chunk representing approximation for an upcoming decision. The curvature of each chunk was weighted with current velocity to produce a velocity set point. The velocity set point was then fed to a bang-bang controller. Taking inspiration from human drivers, the controller either produced 100% brake, acceleration, or nothing. Intermediate values of 0.2 and 0.4 were used if the steering was above certain thresholds to prevent sliding during corners. This agent was used for our round 1 submission of Learn to Race. At this point, we were reaching a limit of what was possible given only the current camera view. Seeing the time difference between our submission and first and second place, we knew we had to implement some form of localization. Traditional mapping and localization techniques we tried were extremely unreliable. We were unable to find reliable visual features using off-the-shelf methods, so we instead started exploring neural network classification models. We ran 3 experiments. Number 1, we tried to classify a current track segment. Number 2, we tried to classify track segments at a much finer scale. And 3, classify user-defined zones. In the top right is a diagram of Anglesey circuit. The red stars indicate midpoint of the finer segments, while coloured boxes indicate manually selected regions. For all experiments, we used an MLP with 2 hidden layers. As input, we used a feature vector extracted from the semantic segmentation network. All experiments were successful, however experiments 1 and 2 required information from the simulator that may not be available during evaluation. Hence, experiment 3 was implemented for use in round 2. This slide shows a pipeline of our agent submitted for round 2. Images are processed by the segmentation model to produce semantic predictions and feature vectors. Semantic prediction is used to compute path coordinates. The feature vector is used by the classification model to predict the current zone. Based on the current predicted zone, a set of control parameters are sent to the steering and acceleration controllers. The steering and acceleration controllers then compute control commands based on current information and parameters. For our localization method, we required a diagram of the racetrack. We found an image in the documents with the race line plotted. We then confirmed coordinates with our first submission. The plot in the upper right shows the zones we selected for our best submission in round 2. Tuning was done using trial and error, analysing log files and intuition gained from the 2 provided test tracks. Here is a short video of our agents. The left uses the location classifier. The right is the agent submitted to round 1 of the competition. The clip shows both agents driving the first segment of the Thruxton circuit. The round 1 agent can be seen applying brakes unnecessarily, and this is due to it being limited by the camera's field of view. As the results show, our team performed well in both rounds of the competition. For reference, the table below shows average kilometres per hour, evaluation location, either local or AIcrowd server, and processing rate in frames per second for each of the circuits. The capital C indicates the use of the location classifier. This concludes the presentation. Thank you for listening, and I hope you found it interesting.